Somewhere beneath the California sun, in a climate-controlled warehouse that hums with the quiet authority of a submarine, a mountain is being consumed, not by fire, not by erosion or decay or the slow indifference of time, by machines, millions of iPhones, the very devices that once glowed in the palms of hands across every continent, that connected lovers across oceans and guided strangers through unfamiliar cities, arrive here in shipping containers stacked in plastic bins like the shed skins of a technological civilization. Each phone is a relic. Each one is a fossil record of human ambition, miniaturized into a rectangle of glass and aluminum, and elements so rare that some of them exist in only a handful of places on the planet. Each one on the, I left to the conventional recycling process that governs the fate of most discarded electronics, would be crushed into an undifferentiated mass of material, its precious components lost forever to the noise of industrial grinding, buried under the next wave of obsolescence. But here, in this facility, something fundamentally different is about to happen. Something that has no true precedent in the history of manufacturing. The machines are waiting, and they have been designed for one singular audacious purpose: to take apart what humanity built and to give it back. The scale of the problem that necessitated this facility is staggering enough to silence a room. Global e-waste, the discarded, broken, and forgotten electronics of nearly 8 billion people, now exceeds 50 million metric tons every single year. That number is not a projection or an estimate hedged by uncertainty. It is a documented fact, verified by the United Nations Environment Program and confirmed by environmental agencies on every inhabited continent. Smartphones sit at the very epicenter of this crisis. They are produced in quantities that strain the rational mind. Well over 1 billion units manufactured annually, assembled in factories that run around the clock, 7 days a week, 365 days a year. And their average lifespan in the hands of a consumer is barely 2 to 3 years before they are replaced by the next generation, slipped into a drawer, handed to a younger sibling, or quietly dropped into a waste stream that was never designed to receive them. What makes this particularly devastating, what elevates it from mere wastefulness to something approaching civilizational recklessness, is what lies inside. A single iPhone contains gold, silver, platinum, copper, cobalt, tungsten, and a constellation of rare earth elements including neodymium and dysprosium, materials that took geological eons to form beneath immense pressure and heat, and that in many cases require the extraction of millions of tons of rock to recover even a few pounds. To simply bury these devices is not just wasteful. It is, by any rational and long-term measure, a profound act of industrial negligence. And it is precisely this negligence that the machines in this room were built to correct. The journey of the discarded iPhone begins at the threshold of this facility, where the phones are fed into carefully organized processing lines, each unit cataloged, scanned, and tracked before it ever comes within reach of a robotic arm. The air inside is filtered to pharmaceutical-grade cleanliness and maintained at a constant temperature, not because the machines themselves are fragile, they are built to endure, but because the materials they are about to recover demand absolute precision. A single contaminant grain lodged in a stream of recovered copper can degrade the purity of an entire batch, rendering it unusable for high-grade applications. This is not a junkyard operation dressed up in clean lighting. This is a laboratory wrapped in the industrial body of a factory, and at its heart, at the center of the choreography, stands the most important machine in the entire operation. Its name is Daisy. Daisy is not a single robot in the conventional sense. It is a system, an integrated architecture of robotic arms, conveyor mechanisms, pneumatic actuators, optical sensors, and thermal imaging arrays, all orchestrated by a central processing intelligence that has been refined over thousands upon thousands of disassembly cycles. The machine occupies a floor space roughly the size of a modest warehouse, and it moves with a fluidity that is almost unsettling to observe for the first time. There is no hesitation in its movements, no visible recalibration, no pause between actions that might suggest uncertainty. Each arm knows precisely where to reach, what to grip, how much force to apply and at what angle to approach, not because it was programmed with a rigid set of instructions for a single phone model, but because it has learned. Sophisticated machine learning algorithms have been fed data from every screw it has ever loosened, every adhesive joint it has ever separated, every battery connector it has ever disengaged, and from that accumulated data, Daisy has constructed an internal mechanical model of the iPhone so detailed that it can account for manufacturing tolerances between different generations of the device and even between individual units produced on separate assembly lines in separate countries on opposite sides of the globe. It is, in the truest sense of the word, an adaptive intelligence applied to the task of disassembly. The first station is the screen. As each iPhone arrives on the conveyor belt, moving at a pace calibrated to match the speed of the robotic arms downstream, an infrared scanner passes over its surface in a fraction of a second. As this scanner reads the thermal signature of the device, whether it is powered or inert, and which model it represents, and feeds that information instantaneously to Daisy's central controller. This is not guesswork or probabilistic estimation. The spectral analysis is absolute. The machine knows with certainty whether it is processing an iPhone 11 or an iPhone 15 Pro, and it adjusts every subsequent action accordingly, because the internal architecture of each generation is subtly but critically different. The screw positions shift. The adhesive compound changes. The battery connector migrates a millimeter in one direction or another. Daisy does not treat these variations as obstacles. It treats them as data, and it adapts. A pneumatic arm descends with surgical deliberation, positioning a heated separation tool along the seam where the display meets the aluminum chassis. The tool is maintained at a temperature precisely calibrated to soften the proprietary adhesive Apple uses to seal the screen. Warm enough to break the bond, but not so hot as to damage the display panel or the delicate ribbon cable that connects it to the logic board beneath. The separation takes less than 2 seconds. The screen does not crack. It does not shatter or warp. It lifts away from the body of the phone cleanly, like a page being turned in a book, and is deposited onto a secondary conveyor where it will be evaluated by a vision system for potential reuse. If the glass is intact and the display circuitry undamaged, it may be refurbished and returned to the market. If it is cracked or scratched beyond recovery, it enters a glass recycling stream where it will be melted and recast into new material. Either way, it is not wasted. But screens are only the first layer. Beneath the glass lies the nervous system of the device, a dense, three-dimensional assembly of components that collectively constitute one of the most sophisticated pieces of engineering ever produced at consumer scale. The logic board, the battery, the camera module, the Taptic engine, the wireless charging coil, the speaker grills, the antenna lines. Each component is soldered, bonded, or mechanically fastened to the others in a configuration that took Apple's own engineers months to design, iterate, and validate. Disassembling it is, in many respects, a harder engineering problem than assembling it in the first place. Assembly can be parallelized. Hundreds of machines working simultaneously on independent subassemblies before they are brought together. Disassembly, by contrast, is inherently sequential. Each component must be accessed in a specific order, because removing one piece without first freeing another risks catastrophic damage, not just to the component itself, but potentially to the machine, or in earlier iterations of this technology, to the human worker performing the task. The battery is the most dangerous element in the entire room, and every aspect of its removal reflects that reality. Lithium-ion batteries are chemically volatile by nature. They store extraordinary energy density in a relatively compact volume, and if punctured, crushed, or subjected to heat beyond their rated tolerance, they can enter a condition known in electrochemistry as thermal runaway, a self-sustaining exothermic reaction in which the battery's internal chemistry accelerates uncontrollably, producing intense heat, toxic gas emissions, and in the most extreme cases, fire or explosive rupture. This is not a theoretical risk. Recycling and waste processing facilities around the world have suffered serious fires traced directly to damaged lithium batteries entering the waste stream without proper handling. Apple's engineers are acutely aware of this danger, which is precisely why Daisy does not crush the battery. It does not grind it, puncture it, or apply uncontrolled mechanical force to it. Instead, a specialized robotic arm equipped with a vacuum-actuated suction gripper and a torque-controlled driver carefully disengages the battery from its adhesive mount. Apple designs its batteries with a flexible adhesive strip, an engineering choice made deliberately to enable non-destructive removal, and Daisy exploits this design feature, peeling the battery away from the board with a controlled vertical motion that never exceeds the mechanical stress tolerance of the lithium cell. The battery is deposited into a dedicated collection container, sealed and routed to a separate processing line, where it will be safely and systematically discharged before its cobalt, nickel, and lithium are recovered. With the battery removed, the logic board remains. And this is where the true depth of the disassembly process reveals itself. The main circuit board, formerly designated as the A-series logic board, is a masterwork of miniaturized engineering. Packed onto a surface area no larger than a postage stamp are transistors numbering in the billions, alongside capacitors, resistors, power management integrated circuits, and the application processor itself, all interconnected by copper traces thinner than a human hair. Soldered and embedded within this architecture are traces of gold, silver, and tungsten at the nanoscale, quantities invisible to the unaided eye, yet significant in aggregate when multiplied across the millions of devices processed through this facility each year. Daisy does not attempt to recover these trace metals at the component level. That task requires entirely different chemistry and will be performed downstream. What Daisy does is extract the board from the phone's chassis with care, ensuring it arrives at the next processing stage structurally intact. A shattered board is a board whose embedded materials become exponentially harder to recover efficiently. The aluminum chassis, the unibody shell that once housed the entire system, is the final major component to be separated. As it passes along the conveyor, an X-ray fluorescent scanner mounted overhead bombards the metal with high-energy photons and measures the characteristic X-rays emitted in return. This technique, known as XRF spectroscopy, reveals the precise elemental composition of the alloy in real time. With an accuracy measured in parts per thousand, Apple uses a proprietary aluminum alloy in its iPhone bodies, and identifying it with absolute certainty allows the recovered material to be directed into the correct downstream recycling stream, a stream engineered to produce aluminum of sufficient purity and grade to be used in the manufacture of new consumer electronics. The disassembly is now complete. Every major component has been separated, identified, and routed, but the transformation, the true industrial alchemy, has only just begun. The components sorted by Daisy flow downstream into a series of specialized processing stations, each one engineered to extract a specific class of material with industrial scale efficiency. The first and most consequential of these stations handles the logic boards. Thousands of boards arrive each hour on automated racks. Down and they are fed into a machine that does something remarkably violent to an object of such extraordinary precision. It shreds them, not randomly or carelessly. The shredder operates with controlled, calibrated aggression, reducing each board to particles within a specific size range, typically between 2 and 5 millimeters, that maximizes the surface area of the embedded metals while keeping the particle dimensions uniform enough for the separation stages that follow to function with consistent accuracy. The sound inside the shredding chamber is visceral and hypnotic, a deep, grinding rhythm punctuated by the sharp crack of epoxy and fiberglass fracturing under sustained mechanical force. It is the sound of extraordinary complexity being deliberately reduced to its most fundamental constituents. The shredded material, a fine, glass dark particulate mixture of fiberglass substrate, cured epoxy resin, copper traces, microscopic gold flakes, silver particles, and fragments of silicon ceramic, is then subjected to a carefully sequenced series of physical and chemical separation processes. First stage is density-based separation, The shredded particles are introduced into a water-based flotation system where differences in the specific gravity of each material cause them to stratify predictably. Precious metals, being among the densest elements on the periodic table, gold at 19 times the density of water, silver at 10, sink rapidly to the bottom of the flotation tank. Lighter materials like fiberglass and polymer fragments float to the surface and are skimmed away for separate processing or disposal. This is not an imprecise or antiquated technique. The flotation tanks are engineered to maintain exact water chemistry, precisely controlled flow rates, and optimal particle suspension levels, and the separation efficiency they achieve routinely exceeds 95%. The dense fraction, now significantly enriched in copper, gold, silver, and other metallic elements, advances to an electrolytic refining stage. Here, material is dissolved in a carefully formulated acid solution, and direct electrical current is passed through the liquid. Under these controlled electrochemical conditions, different metals deposit onto a cathode at different applied voltages, allowing them to be separated from one another with extraordinary purity. Gold, in particular, is recovered through this process to a purity exceeding 99.9%, a grade known in the precious metals industry as 3 nines fine, the same standard demanded by jewelry manufacturers and central banks. The gold recovered from recycled iPhones does not disappear into a vault or a commodity market. It is fed back into Apple's own supply chain, used in the connectors and circuit board traces of devices that will be manufactured months from now. It is, in the most literal and measurable sense, a closed loop. Cobalt tells a different story, and it is one that carries moral weight far beyond the walls of this factory. Cobalt is the element that makes modern lithium-ion batteries chemically viable. It stabilizes the cathode structure, enabling the battery to undergo hundreds of charge and discharge cycles without catastrophic degradation of its internal chemistry. Without cobalt, the portable, high-density power sources that define contemporary electronics simply do not function as we know them, and the overwhelming majority of the world's cobalt supply originates from a single geographic region, the southeastern provinces of the Democratic Republic of the Congo. The conditions under which cobalt is extracted there have been extensively documented by international human rights organizations over the course of decades. The mining is often artisanal, performed by hand, and in numerous documented cases by children. It is one of the most troubling ethical dimensions embedded within the supply chain of modern technology, a shadow that falls across every smartphone, our electric vehicle battery, and laptop sold in the developed world. When Apple recovers cobalt from the batteries of recycled iPhones, it is not merely performing a chemical extraction. It is attempting, in a measurable and verifiable way, to reduce demand for cobalt mined under those conditions. The quantity recovered here, measured in kilograms, is modest against the thousands of tons consumed annually by the global battery industry. But it is not nothing. And in an era of increasing regulatory and public scrutiny on the ethical provenance of raw materials, even modest displacement carries significance. The rare earth elements present their own recovery challenge, one that demands patience and chemical precision. A neodymium and dysprosium, the two rare earths most critical to the permanent magnets that power the Taptic engine and the speakers of an iPhone, are present in quantities measured in milligrams per device. Recovering them efficiently from a matrix of shredded fiberglass and epoxy requires hydrometallurgical processing, dissolving the particulate material in selective acid solutions and then precipitating the rare earths out of solution through careful pH adjustment and the introduction of specific chemical reagents. The process is slow by the standards of industrial throughput, and it requires continuous monitoring by spectrometric instruments that confirm the purity and composition of the output at every stage. But the environmental rationale is compelling. Rare earth mining is among the most ecologically destructive forms of mineral extraction practiced on Earth, producing vast quantities of radioactive waste, toxic tailings, and contaminated groundwater. Every milligram of neodymium or dysprosium recovered in this facility is a milligram that does not need to be torn from the ground. Glass, copper, and aluminum complete the material cycle. The recovered glass, stripped from millions of display panels, is melted and recast. though rarely at the optical clarity and dimensional precision required for a new smartphone display. It finds renewed purpose instead in adjacent industries, automotive windshields, architectural glazing, or as a feedstock for fiberglass insulation. Copper, recovered from circuit traces, charging cables, and connector pins, is refined to electronic grade and returned to the broader supply chain. Aluminum, sorted by alloy composition and fed into electric arc furnaces, is remelted at a fraction of the energy cost required to produce virgin aluminum from bauxite ore, a primary smelting process that, in its conventional form, consumes staggering quantities of electricity and generates significant carbon dioxide emissions as a byproduct. And so, the circle closes. The iPhones that arrived in shipping containers, worn and scratched and declared obsolete by the relentless cadence of annual product cycles, have been taken apart with precision, sorted with intelligence, and reduced to their essential elements. Gold flows back into the connectors of future devices. Cobalt returns to battery cathodes. Aluminum becomes chassis again. Rare earths find their way back into the magnets that make vibration and sound possible. Glass is reborn into new forms. The material that was once discarded is now, through the intervention of machines like Daisy, circulating. But the story cannot end here, because this facility in California is not the conclusion of an ambition. It is the proof of concept. Apple has publicly and repeatedly committed to the goal of achieving a fully closed-loop supply chain, a model in which every material used in the manufacture of a device is eventually recovered, refined, and reused indefinitely, with no requirement for virgin resource extraction. It is an ambition so structurally radical that it challenges the foundational assumption upon which industrial civilization has operated for the better part of 2 centuries, that manufacturing is, by definition, a consumptive act, that progress requires extraction, that the products of human ingenuity are ultimately disposable. The obstacles between here and that vision are formidable. Consumer behavior remains deeply entrenched in disposability. The economics of virgin material extraction, subsidized in many regions by governments and underpriced by markets that do not account for environmental externalities, still favor primary sourcing over recycling in many material categories. The technical limitations of current recovery processes mean that not every element can be efficiently extracted, and not every recovered material meets the purity thresholds demanded by high-performance applications. And the energy required to run facilities of this scale, to power the robotic arms, the shredders, the flotation tanks, the acid bath, all the spectrometers, and the furnaces, is itself a significant environmental cost that must be honestly weighed against the benefit of material recovery. And yet, the trajectory is unmistakable. The machines are learning faster than they did a year ago. The processes are refining with each cycle. The volume of material flowing through these facilities is increasing. The regulatory environment in both Europe and the United States is beginning to mandate repairability, recyclability, and extended producer responsibility in ways that were unimaginable a decade ago. The economic case for recovered materials is strengthening as geopolitical instability disrupts traditional mining regions and as the true environmental cost of extraction begins to be priced into global commodity markets. In the end, Daisy and the systems built around it represent something larger than any single recycling operation. They represent a reckoning, quiet, technical, and conducted under fluorescent lights, but a reckoning nonetheless. A civilization that has built its prosperity on the assumption of infinite natural abundance is beginning, slowly and imperfectly, and with full awareness of how far it has yet to go, to confront the consequences of that assumption. And here, in a climate-controlled warehouse, where robotic arms move with the precision of surgeons and chemical baths, dissolve the remnants of billions of human decisions, the first serious, scalable answer to that confrontation is being written, one discarded iPhone at a time.